Question 10. A cube of uniform density has size of length 2 centimeters, so it's a 2 centimeter by 2 centimeter by 2 centimeter cube, and a mass of 12 grams in its rest frame, so it's not moving. Calculate the cube's density. Density is of course mass per volume. So mass is 12 grams, what's the volume? Well, it's going to be 2 cubed, because we've got a cube. So we end up with 12 grams over 2 by 2 by 2, and that of course is 8 centimeters cubed. So we end up with 1.5 grams per cubic centimeters. Now part B is going to ask something a little different. Calculate the cube's density when it is moving at 60% of the speed of light. So in this case, we're going to have to worry about length contraction and mass dilation. Because once the cube starts moving, it is no longer a cube. Instead, it is a square prism, right? These lengths are going to be perpendicular to the direction of motion, so they won't change. The only distance that will change is going to be this one. And because of length contraction, it'll be shorter than 2 centimeters now. Luckily, we know exactly how much it's going to change by. Now, the volume isn't the only part of the cube that's going to change. We have mass dilation to worry about too. That means that our 12 grams is going to change. So, let's write down an expression for the density of the cube now. We have mass over volume equals the relativistically dilated mass times the contracted length of the cube and then the normal length of the cube, which haven't changed. This makes sense, right? This part of the equation is the volume, and the first fraction is the mass. Now hang on. We have in these two denominators 2 square roots which contain the same thing. So what happens if we multiply 2 square roots by each other? Say we have the square root of y times the square root of y. We're going to end up with y. Right? This means that we can get rid of the square root around these two parts of the denominator. That makes sense, right? So we've moved the m0 over to the right, because m0 times 1 is still m0. On the bottom, we've still got the 3 L0s, and we've multiplied these two factors together and gotten rid of the square root. Now hang on, this looks familiar. This is the answer that we calculated in the first part of the question. It's just 1.5. Right? So now all we need to do is substitute our 1.5 and then our velocity into the left side of the equation, or rather the left fraction in the equation. So there's our 0.6, we're squaring it of course, and our 1.5 grams per centimeter, per cubic centimeter that we already calculated, and this will evaluate to 1.5625 times our original density, which gives us an answer of 2.34 grams per cubic centimeter. So we can see that our density increases not by just that factor that we're used to, but by that factor squared. So we get a little bit more of an increase in density than we would have expected if we were only using length contraction or only using mass dilation. Well, that's the end of the questions. In this section, we've covered mass dilation, what it is, how it arises, and quantitatively, exactly how it changes when we move at high speeds.